200 million years ago, in a warm sea that has no name because there was no one to name it, something the length of a bus hung motionless 100 meters down in the blue-black dark below the reach of the sun, waiting. It was not a fish, though it had the shape of one. It was not a whale. There would be no whales for another 130 million years. It breathed air, and it had come from ancestors that once walked on land, and it had given all of that up. The legs, the ability to leave the water, the need ever to touch the shore again. It gave birth in the open ocean to live young that had never known anything but water. Its eyes were the largest of any animal that has ever lived, each one the size of a dinner plate. And they were open now, in the dark, gathering the last of the light, watching for the faint silver shimmer of a squid moving far below. It was one of thousands of kinds of animal that ruled these seas for 180 million years. Not one of them survives today. Every lineage in the water tonight is one that came afterward into the space they left. Tonight, we are going to spend some time in their ocean. Welcome to Lost Ages. Over the next few hours, we're going to sink into the seas of the Mesozoic, the long stretch of warm, high, crowded ocean that lay over this planet through the entire age of the dinosaurs. But we're not going to spend our time on the land. The dinosaurs can have the land tonight. We're going underneath, into the water, where a completely separate empire rose and fell across the same 180 million years, ruled by animals that have no living descendants and no modern equal. We'll meet the reptiles that walked back down into the sea and rebuilt themselves from the ground up into something that could never come ashore again. The fish-shaped hunters with the enormous eyes. The four-flippered rowers with necks longer than their bodies. The short-necked giants with 2-meter skulls and the strongest bite ever measured. The crocodiles that gave up their armor and grew a fish's tail. And the lizards, actual lizards, cousins of the things in your garden, that took over every ocean on Earth in 30 million years and then vanished in a single morning. Before we go under, 2 small things. If you find something here worth staying for, a like helps more than you'd think. And if these are the kind of journeys you'd like more of, you're welcome to follow along. And there's one thing I'm always curious about. In the comments, tell me where you're listening from, your city, and what time it is there right now. These recordings travel much further than I ever expect them to, and I like knowing which part of the world has gone dark while this one is playing. Before we go under and meet the animals, it's worth spending a moment on how we know any of this at all. Because the honest answer is that the Mesozoic Sea comes to us through a handful of extraordinary windows, and everything we're about to picture is reconstructed from what those windows preserved. Most of the seafloor of most of history is lost to us. The ocean floor is constantly being recycled, dragged down into the Earth's interior at the edges of continents, remade at the mid-ocean ridges. So the actual bed of most ancient seas is simply gone, subducted and melted hundreds of millions of years ago. What survives is the sediment that happened to be laid down on the shallow shelves and inland seas that later became dry land, lifted up and exposed where we can reach it. We are not looking at the deep Mesozoic ocean. We are looking at its shallow edges, the parts that got stranded on continents when the seas withdrew. And within those surviving sediments, only a few places preserved soft, delicate, complete animals rather than scattered bones. These exceptional sites, the fine-grained shales and lagoonal limestones where conditions were just right, are the windows, and a surprising amount of everything we know comes through a small number of them. There is a quarry region in southern Germany, laid down in a still, warm, oxygen-starved lagoon, where the bottom water was so lifeless that carcasses sinking into it were neither scavenged nor disturbed. The fine lime mud closed over them and held them, and it held not just bones but outlines. The soft body shapes of ichthyosaurs, the position of the fins, the wrinkles of skin, the unborn young inside the mothers. Almost everything we know about what an ichthyosaur actually looked like, as opposed to what its skeleton looked like, comes from places like this. There is the crumbling coast of southern England, where 2 centuries of erosion have been steadily releasing marine reptiles from blue-gray cliffs, one winter storm at a time. There is the chalk of the American plains, the floor of that inland sea, dense with articulated skeletons and preserved last meals. And there are scattered others around the world, each one a keyhole into a particular sea at a particular moment. Piece them together across the whole Mesozoic, and you can assemble something like a continuous picture. But it's worth remembering that it is assembled, stitched together from a small number of lucky preservations, with enormous gaps between them that we fill with inference and comparison and careful guessing. So when I describe this ocean to you tonight with confidence, the hunting, the birth, the daily rhythm, understand that the confidence is earned but partial. We are reconstructing a 180 million year empire from a handful of windows. The wonder is not that there are gaps. The wonder is how much, from so little, we can actually see. Now, let the room settle around you. Let the day you've finished, everything it asked of you, everything it didn't quite give back, sink away somewhere behind you where it can wait until morning. We're going back to a warmer world. A world with no ice at either pole, no voice anywhere on it, and a sea that went on almost without end, full of things that will never exist again. The water is warm. Let yourself down into it. To understand why these seas produced such monsters, you have to understand first that the Mesozoic ocean was a fundamentally different kind of place from the one that covers the planet now. And almost every difference ran in the direction of abundance. Start with the temperature. There was no permanent ice anywhere on Earth for most of this era. Not at the North Pole, not at the South. The poles were cool, temperate, forested, but not frozen. Crocodile relatives lived at latitudes that are now buried under Arctic tundra. And with no ice locking up the planet's water, sea levels stood far higher than they do today. At the peak, more than 170 meters higher, sometimes considerably more. Think about what that does to a continent. Today, the edge of the land drops fairly quickly into deep water, and the shallow, sunlit, productive zone around each landmass is a relatively narrow band. Raise the sea by 170 meters, and the ocean climbs up over the low interiors of the continents, flooding vast areas that are dry land today. Enormous shallow seas spread across the middle of North America, across most of Europe, across northern Africa and the Middle East and Central Asia. Warm, sunlit, shallow water in a quantity the modern world simply does not have. And shallow sunlit water is where the ocean does its living. Sunlight only penetrates the top layer of the sea. Below a couple of 100 meters, photosynthesis stops. So the productive part of any ocean is its thin, illuminated skin. And the Mesozoic had far more of that skin than we do, spread thin across drowned continents, warm from pole to pole. More warm, shallow sea means more plankton. More plankton means more of the small animals that eat plankton. More small animals means more of the medium animals that eat them. And more medium animals means the ocean can support very large predators at the top. More of them, and bigger than a colder, deeper, less productive ocean could ever carry. That is the first reason the Mesozoic bred monsters. The base of the food chain was enormous, and a food chain with a huge base can afford a very heavy top. There's a second reason, and it has to do with what was missing. For the entire span of this era, from around 250 million years ago to 66, there were no marine mammals, no whales, no dolphins, no seals, no sea lions. The lineages that would eventually produce those animals were, throughout the Mesozoic, small land creatures scurrying through the undergrowth at night, staying out of the way of the dinosaurs. Not one of them had gone anywhere near the water in any serious way, which means that every large predator role in the sea, every niche that is filled today by a whale or a dolphin or a seal or a large shark, was standing open, available, unclaimed by any mammal. And into that vacancy came the reptiles. This is the thing that makes the Mesozoic ocean so strange and so worth visiting. The roles are familiar. There is a deep-diving squid hunter, exactly as there is today. There is a fast, open-water pursuit predator. There is an ambush hunter, a shellfish crusher, a filter feeder, a coastal generalist, an apex giant at the very top. Every one of those jobs existed then as now, but the animals filling them were built on a completely different chassis. Cold-blooded ancestry, scaly skin, a reptilian body plan. And so they solved the same problems in unfamiliar ways, and the results look like nothing alive. A dolphin and an ichthyosaur do the same job and have nearly the same shape, and they are not related in any way that matters. The ichthyosaur got there 100 million years earlier, from a lizard-like starting point, by pure convergence. When you look at the Mesozoic Sea, you are looking at a complete, functioning ocean ecosystem that ran the same machinery as ours, staffed entirely by animals from a different branch of the tree of life. It is the closest thing this planet has ever produced to an alien ocean. And it was right here. Let's build the world properly, because we're going to be living in it for the next few hours. The single supercontinent, the one great landmass that had assembled at the end of the Paleozoic, was breaking apart throughout the Mesozoic, slowly, along rifts that filled with sea as they opened. At the start of the era, the continents were still mostly joined. By the end, they had drifted into something approaching their modern arrangement, with young oceans widening between them. Every one of those widening gaps was new marine habitat, new coastlines, new shallow shelves, new basins for life to spread into. The climate was, by our standards, a greenhouse. Carbon dioxide levels ran several times higher than today. The whole planet was warm and humid, and the temperature difference between the equator and the poles was far gentler than the brutal gradient we have now. There were no roaring circumpolar currents, no cold deep water formation of the kind that drives the modern ocean's circulation. The Mesozoic Sea was warmer all the way down, more sluggish, more uniform. And periodically, That came with a cost we'll return to, because warm water holds less oxygen, and several times during this era the deep ocean simply ran out of it. But in the good stretches, and there were tens of millions of years of good stretches, the Mesozoic ocean was as rich as any sea the planet has ever held. Reefs ran along the tropical shelves, built at first by corals and later, strangely, by clams that had turned themselves into reef-building tubes. The open water was thick with coiled ammonites in numbers that are genuinely difficult to imagine. Their shells so abundant in the rock today that whole limestone beds are made of almost nothing else. Squid-like belemnites moved in shoals. Fish of every size filled the water column. And moving through all of it, at every depth, were the reptiles, the small ones near the surface, the deep divers below, the coastal ambushers in the shallows, and the giants cruising the open blue. One more thing about this world before we begin to meet its inhabitants, because it changes how you'll picture everything that follows. There was no sound in it that any animal had made on purpose to communicate over distance. Or if there was, we have no evidence of it. The Mesozoic Sea was, as far as we can tell, largely silent in the way the modern ocean is not. Today, the sea is full of deliberate sound, the songs of whales carrying for hundreds of kilometers, the clicks of dolphins and sperm whales echolocating in the dark, the chorus of fish and snapping shrimp. All of that came later, with the mammals. The reptiles of the Mesozoic hunted, as far as we know, largely by sight and by smell and by the pressure sense that all aquatic vertebrates carry along their flanks. Not by broadcasting and listening for sound the way the modern deep ocean does. So when you picture this ocean, picture it quiet. A vast, warm, blue-green world, full to the brim with life and nearly silent. No songs in the deep water, no clicks in the dark, just the enormous slow movement of enormous animals through water that carried no voices. It stayed that way for 180 million years, and then it ended in a single morning, and everything in it died, and the silence became total for a while before a different kind of animal came down and filled the water with sound. But that's the last chapter. We have a long way to go before then, and the first thing we need to understand is how any of these animals got into the water at all. Because every one of them came down from the land, and going back into the sea is one of the strangest things an air-breathing animal can decide to do. There is a final quality of this sea I want to give you before the ending, and it is the hardest to convey, because it is an absence rather than a presence. The strangeness of a warm ocean with no ice anywhere in the world. We live on a planet with frozen poles. It shapes everything about our oceans. The cold, dense water that sinks at the poles and drives the deep circulation. The great temperature gradient from equator to pole that powers the currents and the weather. The cold, oxygen-rich, deep water that ventilates the abyss. Our entire ocean is organized around the fact that its ends are frozen. We take it as simply how oceans are. For most of the Mesozoic, it was not how oceans were. There was no permanent ice at either pole for tens of millions of years at a stretch. The poles were cool and temperate, not frozen, forested, inhabited, mild. And an ocean with warm ends is a fundamentally different ocean. The water is warmer all the way down. The circulation is more sluggish. The deep sea is less well ventilated, more prone to the oxygen collapses we've talked about. The temperature difference between the tropics and the poles is gentle rather than brutal. It is a calmer, warmer, more uniform sea, top to bottom, pole to pole. Picture what that means for the animals. A marine reptile could range from the equator to the far north or south without ever crossing the brutal thermal barriers that structure our ocean. The warm, shallow seas spread far toward the poles. Life extended into latitudes that are frozen wasteland today. The whole habitable envelope of the ocean was larger, warmer, and more continuous than anything we know. A single vast warm sea wrapped around a planet with no ice on it anywhere, full from end to end with enormous animals. It is genuinely difficult to picture because we have never seen it. Every ocean any human has ever known has had frozen poles. But for the animals of this story, the warm, iceless sea was simply the world, the only world, and it lasted, in one form or another, for most of 180 million years. The cold, ice-bound ocean we think of as normal is, in the long view, the strange one, the recent one, the exception. The Mesozoic Sea, warm from pole to pole, iceless, sluggish, and full, was the sea these animals were built for, and it is as alien to us now as anything on another world. Let that be part of the picture you carry down. Not just the monsters, but the water they moved through. Warm everywhere, iceless everywhere, stretching unbroken from a temperate pole to a temperate pole, holding its enormous silent empire in a global warmth we have never known and can barely imagine. It's worth pausing on the sheer span of time we're moving through, because the numbers slide past too easily and the mind refuses to hold them. And without holding them, you can't feel what this ocean actually was. The Mesozoic lasted about 186 million years. Try to place that against something you can feel. Anatomically, modern humans have existed for roughly 300,000 years. The entire history of our species, from the first people to tonight, would fit into the age of the dinosaurs' oceans more than 600 times over. The whole of recorded human history. Everything since the first writing, every civilization, every war, every book, is about 5,000 years, which is to the Mesozoic as a single second is to most of a year. Now think about what that means for the animals in it. The gap between the earliest ichthyosaurs and the last of them is longer than the gap between the last ichthyosaurs and us. When a Jurassic pliosaur cruised its warm sea, the first marine reptiles were already as ancient to it as the dinosaurs are to us. Deep prehistory, unimaginably long ago, animals of a vanished earlier world. These lineages did not flicker briefly. They ran for tens of millions of years each, longer than most of them are easy to comprehend, rising and diversifying and fading across spans of time that dwarf the entire history of mammals on land. And the sea held all of it, continuously. There was never a gap. From the first Triassic reptile easing into the shallows to the last mosasaur dying under a darkening sky, the empire of the marine reptiles was unbroken. 180 million years of warm water, full of enormous animals, generation after generation after generation, each one living and hunting and giving birth and dying, without any sense that it was part of an era, or that the era would end. We compress it, tonight, into a few hours. We move from the Triassic to the Cretaceous in a sentence, But every one of those sentences covers more time than the mind can honestly hold, and every animal in them lived a full life inside that time, in the warm, silent water, exactly as real to itself as you are to yourself right now. Hold that, if you can, as we go down. Not a museum, not a diagram. A real ocean that really existed for almost unimaginably long, full of real animals living real days. And all of it now gone, except for the shells and bones and the faint marks of teeth and the reconstruction we are about to swim through together. There is something almost perverse about an air-breathing animal going back into the sea, and it's worth sitting with the strangeness of it before we watch it happen, because it happened over and over throughout this era, and each time it was a small act of undoing. Consider what the ancestors of these animals had already achieved. Life had crawled out of the water in the first place across an enormous span of time, acquiring at great cost every piece of equipment needed to survive on land. Lungs that could pull oxygen from air, legs that could bear weight against gravity, a skin that held moisture in rather than letting it leak away, eggs with shells so that reproduction no longer required a body of standing water. Every one of those was a hard-won solution to the problem of living out of the sea, refined over tens of millions of years. And then, at the start of the Mesozoic, some reptiles took all of that equipment and walked back down the beach into the water, where most of it became a liability. In the sea, lungs are a problem. You have to keep returning to the surface to breathe, interrupting everything, always tethered to the boundary between two worlds. Legs are a problem. They're poor paddles, and weight-bearing architecture is dead weight in water. Watertight skin still has to deal with the constant osmotic pull of salt. And eggs with shells are the worst problem of all, because a shelled egg has to be laid on land, in air, which means an animal that is committed fully to the water can no longer reproduce without crawling back out of it. And an animal built for swimming is helpless on a beach. So why do it? Why undo 130 million years of adaptation to the land? The answer is always the same, and we saw it at the end of the last episode if you were here for that one. Animals don't move backward, because backward is better in principle. They move toward food that nothing else is eating. And at the start of the Mesozoic, the sea was the emptiest it had been in 250 million years. The reason the sea was empty is one of the most important facts in this entire story, so let's be clear about it. Just before the Mesozoic began, the ocean had been through the worst catastrophe in the history of life. An extinction so severe that something like 4 out of every 5 kinds of marine animal were wiped out. The great predators of the previous era were gone. The reefs were gone. The food chains had collapsed and were slowly, over millions of years, rebuilding from the survivors. By the early Triassic, the first period of the Mesozoic, the base of that food chain had recovered enough to be productive again. There were fish. There were shellfish. There were swimming invertebrates in growing numbers. But the top of the food chain was still empty. All the large marine predators that would normally eat those fish and shellfish had died in the catastrophe and had not been replaced, because it takes far longer to evolve a large apex predator than it does to rebuild a population of small prey animals. So here was the situation around 250 million years ago. A sea filling up with food and almost nothing large enough to eat it. A standing invitation. An entire trophic level, the most valuable real estate in the ocean, vacant and waiting. Meanwhile, on land, life was hard. The early Triassic supercontinent was hot, harsh, and violently seasonal, its interior a desert thousands of kilometers from any coast. For a coastal reptile scraping a living at the edge of the land, the water just offshore, full of fish, empty of anything that might compete for them, must have been an almost irresistible opportunity. They took it. Not once, but many separate times, in many separate lineages, over the following tens of millions of years. And we can watch several of those transitions happen in the fossil record, caught partway through. The earliest ones are the most touching because they are so obviously incomplete. Animals caught in the act of committing neither one thing nor the other. There is a small creature from the early Triassic of what is now China, around half a meter long, that shows the transition at almost its very beginning. It has a short snout, a stubby body, and limbs that are not quite legs and not quite flippers. Something in between, webbed and broadened, but still clearly derived from a walking foot. Its most telling feature is its bones. They are unusually thick and dense, far heavier than a land animal's bones need to be. That density is ballast. It let the animal sink and stay down in shallow water without constantly fighting its own tendency to float, hovering just above the bottom, drawing in soft prey with a suction bite. It is not a land reptile that occasionally swims. It is not yet a sea creature. It is something 1 or 2 million years into a journey, still able to haul itself out, already spending most of its life in the water. If you could hold it in your hands, you would not be able to say which world it belonged to, and neither, in a sense, could it. From starting points like this one, several completely separate lineages of marine reptile radiated outward through the Triassic Sea in what was, for a few tens of millions of years, an extraordinary open experiment in how many different ways a reptile could be aquatic. Most of the experiments were dead ends, and they are worth a moment each because they show how wide the possibilities were before the winners emerged. There were the placodonts, which are among the strangest reptiles ever to have lived. They had barrel-shaped bodies, short limbs, and mouths built for a single purpose, crushing shellfish. Some had protruding front teeth like a set of blunt tusks for prizing clams and other shelled animals off the rocks, and behind them, on the roof of the mouth, broad, flat plates of tooth for grinding the shells to fragments. Several placodont lineages independently grew heavy, bony armor across their backs, converging so closely on the shape of a turtle that the first specimens found were mistaken for turtles. They spent 40 million years doing essentially nothing but eating clams in shallow tropical lagoons, and then they were gone. There were the plesiosaurs, long and flattened, with strange downturned snouts, whose way of life is still argued about. And there was one animal that is simply difficult to believe when you first encounter it. It was around 6 meters long, and more than half of that length was neck. Not a flexible, curving, swan-like neck, but a stiff one, held out straight, supported by only about a dozen enormously elongated vertebrae, some of them individually longer than the animal's entire skull. At the end of this rigid pole sat a small head. Behind it, a compact body and a long tail. For a long time, no one could work out what it was for. A neck like that is a structural nightmare. It cannot be lifted against gravity on land. Swung through water, it would be slow and exhausting. The current best guess is that the animal was an ambush hunter that used its neck as a kind of reverse fishing rod, keeping its body hidden in a rock crevice or in murky water while the small head crept forward on the end of that long, stiff pole, easing into a school of fish that never noticed the huge body attached to it because the body was too far away to see. And we know how at least 2 of these animals died because their fossils have been found with the neck bitten cleanly through and the head end missing entirely. Something large came along and removed the fishing rod from the fisherman. These were the sideshows, the strange, specialized experiments that ran for a while and then closed. There is one more transitional group worth meeting before we leave the Triassic, because it is the ancestral stock of the plesiosaurs, and because it shows the four-flippered body plan being assembled before our eyes. The nothosaurs were long-bodied, long-necked marine reptiles, but unlike the fully committed swimmers we've met, they still had 1 foot, quite literally, on the land. Their limbs were webbed feet rather than true flippers, and their body was still capable of movement ashore. They were, in all likelihood, amphibious in the way a sea lion is amphibious today, hunting in the water, powerful and agile there, but hauling out onto rocks and beaches to rest and to breed. Picture one on a Triassic shore. A long, low, streamlined reptile, a couple of meters of it, glistening wet, dragging itself up onto a warm rock to bask, its webbed feet splayed, its long neck curved back over its body. In the water, it was a hunter, sinuous and quick, snapping up fish with a mouthful of long, interlocking teeth. On land, it was clumsy but functional, still tied to the shore, still laying its eggs there, still belonging partly to both worlds. The nothosaurs are important because they are the bridge. They sit in the fossil record between the early, tentative marine reptiles and the fully committed plesiosaurs that would follow. And in their bodies, you can see the plesiosaur being drafted. The long neck is beginning. The paddle limbs are on their way. The commitment to the water is deepening, generation by generation, though it is not yet complete. From something very like a nothosaur, over the course of the late Triassic and into the Jurassic, the plesiosaurs emerged. And in doing so, they crossed the line the nothosaurs never quite crossed. They gave up the webbed feet for true wing flippers. They gave up the amphibious body for a fully aquatic one. They gave up the shore entirely and began, like the ichthyosaurs before them, to give birth in the open water. The nothosaur was a reptile that lived in 2 worlds. Its descendant, the plesiosaur, chose one of them and never came back to the other. It is a small story. The nothosaurs, easy to skip past on the way to the more spectacular animals. But it is worth a moment because it shows the machinery of the whole era working in slow motion. The land animal becoming a sea animal, one adaptation at a time, across millions of years, until one day a lineage crosses a line and can never return. It happened to the ichthyosaurs' ancestors. It happened to the plesiosaurs' ancestors through the nothosaurs. It happened to the mosasaurs' ancestors and the metriorhynchids' ancestors. Over and over, the same slow crossing, the same closing of the door behind them. The Mesozoic sea was full of animals that had, at some point in their deep ancestry, made a decision they could not take back. But alongside them, 2 lineages were emerging in the Triassic Sea that would not close. 2 body plans that worked so well they would define the next 180 million years. One of them was becoming a fish. The other was learning to fly underwater. We'll take the fish-shaped one first, because it went further than any reptile has ever gone toward abandoning the land entirely, and because it had the largest eyes the world has ever seen. Their name means, quite literally, fish lizard, and it is one of the few scientific names that tells you exactly what you're looking at. They began as lizard-like reptiles, and they became, over the course of the Triassic, as close to a fish as an air-breathing animal has ever managed to get. The transformation was more thorough than in any other marine reptile group, before or since. By the time it was complete, an ichthyosaur had a streamlined, torpedo-shaped body indistinguishable in silhouette from a fast open-ocean fish. Its limbs had been reduced to stiff, wing-like flippers, the internal bones shortened and multiplied into a dense mosaic of little discs packed inside a smooth paddle. It had grown a triangular fin on its back that contained no bone at all. Pure soft tissue, invisible in most fossils, and known only because a handful of specimens from a particular fine-grained German shale preserved the animal's whole body outline as a dark film in the rock. And at the back, it had grown a crescent-shaped tail fin held vertically, with the spine bending sharply downward to support the lower lobe. Look at a dolphin. Look at a tuna. Look at a reconstructed ichthyosaur. The three are near identical in overall shape, and none of them is closely related to the others. A mammal, a fish, and a reptile, arriving at the same body from three completely different starting points. This is one of the clearest lessons the fossil record has to teach. When the problem is, move fast and efficiently through open water for a very long time, there is essentially one right answer, and evolution finds it again and again, no matter what it has to work with. The ichthyosaurs found it first, by more than 100 million years. Two things about these animals deserve to be dwelt on, because they are the details that turn a diagram into a living creature. The first is the eyes. Ichthyosaurs had, relative to their body size, and often in absolute terms, the largest eyes of any vertebrate that has ever existed. One well-known genus had eyeballs around 23 centimeters across, roughly the size of a dinner plate, set into a skull that was not, by the standards of these animals, especially large. Another, a giant from the Triassic, may have had eyes larger still. We know their size directly, and this is one of the small miracles of fossilization. The ichthyosaur eye was braced by a ring of bony plates set into the eyeball itself, encircling the iris. A structure called a sclerotic ring, which shows up clearly in well-preserved skulls. The ring had two jobs. It held the huge eyeball in shape against the pressure of the water, and it helped adjust the focus of the lens. And because it's made of bone, it fossilizes, and we can measure it, and from it we know exactly how big the eye was. An eye that size is not the eye of an animal that hunts in bright surface water. There is far more light near the surface than any eye needs. An eye that large is a light-gathering instrument built to function where light is scarce, at depth or at night. And there is corroborating evidence. The bones of some ichthyosaurs show the characteristic pitting and damage caused by repeated deep diving, the same kind of decompression injury that shows up in the bones of modern deep-diving whales and seals. So the picture assembles itself. These animals were going down, hundreds of meters down, into the blue-black twilight where the sun barely reaches, hunting squid and fish in near darkness, with eyes evolved to catch every last available photon. The dinner plate eye at the start of tonight's program, hanging motionless in the dark and watching for a silver shimmer below, was doing exactly what it was built to do. The second thing is how they were born. An air-breathing animal that has committed completely to open water faces a reproductive crisis. And it is the same crisis for every lineage that ever made the commitment. Eggs have to be laid somewhere the embryo won't drown, and an animal that can no longer crawl onto a beach has nowhere to lay one. The ichthyosaurs solved it in the only way it can be solved. They stopped laying eggs altogether and gave birth to live young, in the water, the way whales and dolphins would independently learn to do more than 100 million years later. We know this beyond any possible doubt because we have the fossils, and some of them are almost unbearably vivid. There are ichthyosaur skeletons with the tiny skeletons of unborn young preserved inside the body cavity, sometimes several at once. And there is one specimen from the fine shales of Holzmaden in Germany that stops you cold when you understand what you're looking at. An adult female preserved in the act of giving birth. One baby is still inside her. One is halfway out, and one is already free of her body in the water. She died in the middle of delivery 200 million years ago and was buried so quickly and so gently in fine mud that the entire moment held, frozen, across all that time for us to find. There is a further detail in these birth fossils that is quietly extraordinary. The earliest ones show the young emerging head first, which is the pattern for land vertebrates. Later ones show the young emerging tail first, which is what whales and dolphins do. Because in a slow underwater birth, coming out tail first keeps the newborn's head and its first breath for last, reducing the risk that it drowns during delivery. You can watch, across the fossil record, an entire lineage of animals slowly working out the safest way to be born in the open sea, arriving at exactly the same solution the mammals would arrive at, 100 million years early. For all their strangeness, the ichthyosaurs were, for a long stretch of the Mesozoic, simply the most successful large animals in the ocean. Through the Triassic and into the Jurassic, they diversified into a huge range of forms and sizes, from small, fast, dolphin-sized hunters to the true giants of the Triassic, some of which reached lengths rivaling the largest whales, feeding on who knows what in seas we can barely reconstruct. I want to give the giant Triassic ichthyosaurs their own moment, because they are among the most mysterious large animals that have ever lived, and they are usually skipped over on the way to the more familiar Jurassic forms. The classic ichthyosaur, the dolphin-shaped, dinner plate-eyed, 3 or 4 metra hunter, is a Jurassic animal, and it's the one everyone pictures. But earlier, back in the Triassic, before the group settled into that streamlined template, some ichthyosaurs grew to sizes that rival the largest whales, and they did it fast, within just a few million years of the group first appearing. There are remains from the Triassic of animals that may have reached 15, 17, even more metras in length. Enormous, and enormous surprisingly early when the lineage was still young. What these giants ate and how they lived is genuinely uncertain. Some may have been filter feeders of a kind, or hunters of large, soft-bodied prey. The fossils are incomplete, and the debate's alive. but their mere existence tells us something remarkable. That within a geological eye blink of the reptiles first returning to the sea was already rich enough and empty enough at the top to support animals the size of whales. The vacancy left by the great Permian extinction was so complete, and the recovering food web so productive, that giants evolved almost immediately to fill it. There is a site in Nevada, high desert now, seafloor then, where a number of these giant Triassic ichthyosaurs are preserved together, and their arrangement has been argued over for decades. One recent interpretation suggests it may have been a place these animals returned to again and again over long spans of time to give birth. A kind of ancient calving ground where generation after generation of enormous marine reptiles came to bear their young in relative safety, the way some whales return to particular warm lagoons today. If that reading holds, it is an astonishing thing to contemplate. A specific patch of Triassic sea used for the same purpose by the same lineage across enormous spans of time, a tradition of place stretching back 230 million years. These giants faded, and the ichthyosaurs settled into their more familiar dolphin-like form for the rest of their long run. But the Triassic giants stand as a marker at the very start of the era. Proof of how quickly and how completely the reptiles claimed the empty sea. Within a few million years of walking back down the beach, they were already producing animals the size of the largest creatures the ocean has ever held. The empire did not build slowly. It erupted. The classic form, the one most people picture, the one from the German shales, is a beautifully economical animal 3 or 4 meters long, huge-eyed, deep-diving, squid hunting, abundant enough that its remains make up significant portions of certain rock beds. For tens of millions of years, this was one of the default shapes of life in the open sea. If you had lowered yourself into a Jurassic ocean, these are among the animals you would have seen most often. Quick, curious, big-eyed shapes rising and falling through the water column, going down into the dark to feed and coming back up to breathe. And then, through the early Cretaceous, they declined, and around 90 million years ago, well before the asteroid, well before the end of everything else, they disappeared entirely. Why is worth understanding, because it is the quiet moral of this entire series. The ichthyosaurs were superbly, exquisitely specialized, deep-diving open ocean hunters tuned to a particular kind of stable, productive water column, and the Cretaceous seas became unstable. The repeated episodes of deep water oxygen collapse we'll come to later disrupted exactly the conditions they depended on, again and again. Faster evolving fish moved into some of their prey. Newer, more adaptable reptiles moved into some of their niches. And the fish lizards, the 200-million-year-old lineage with the dinner plate eyes, simply could not adjust fast enough and went out. Not with a catastrophe, but with a slow squeeze. The specialists lost. They almost always do in the end. But the space they left did not stay empty for long, and to see what came into it, we need to go back and pick up the second great lineage, the one that, instead of becoming a fish, learned to fly. There is a broader lesson hiding in the ichthyosaur's fate, and it runs underneath every chapter of this story, so it's worth naming clearly now, because you'll see it happen again and again tonight. The animals that dominate an ocean are almost never the animals that survive it. Think about what dominance actually requires. To become the ruling form in a rich, stable sea, an animal has to specialize. To become superbly, precisely adapted to a particular way of making a living in a particular set of conditions. The deep-diving ichthyosaur tuned to a stable, productive water column. The pliosaur, built around a 2-meter skull and a specific kind of large prey. The reef-building rudest clam, perfectly suited to warm, shallow tropical shelves. Specialization is what dominance is made of. You get to the top by being exquisitely good at one thing. But specialization is a bet. It is a wager that the conditions you are adapted to will continue. And for millions of years at a time, that bet pays. The deep water stays stable. The large prey stays abundant. The tropical shelves stay warm. And the specialist thrives and dominates and drives the generalists to the margins. And then the conditions change. And when they change, the exquisitely adapted specialist has nowhere to go. Its whole body, its whole way of life, is a solution to a problem that no longer exists. The very adaptations that made it dominant become the things that kill it. Meanwhile, the unimpressive generalist at the margins, the tolerant one, the one that could eat anything and live anywhere and never got very good at any single thing, rides the change out on almost nothing and inherits the emptied sea. We saw it with the ichthyosaurs, squeezed out by instability before the asteroid even arrived. We'll see it at the very end when the asteroid takes the specialists. The ammonites with their delicate planktonic young, the mosasaurs at the top, and spares the tolerant survivors. It is one of the deepest patterns in the history of life, and the Mesozoic Sea demonstrates it over and over. Being the best adapted animal in the ocean is a wonderful thing to be, right up until the ocean changes, at which point it becomes the worst. There is something almost consoling in it if you turn it over. The monsters were not defeated by better monsters. They were undone by change itself, by the one thing nothing can adapt to in advance, because it hasn't happened yet. And the meek did, in a very literal sense, inherit the sea. Not because they were better, because they were less committed. If you asked 100 people to draw a sea monster, a good number of them would draw a plesiosaur without knowing its name. The small head, the impossibly long neck, the broad barrel body, the 4 wide flippers, the whole silhouette rising out of the water like the thing people claim to see in cold northern lakes. It is the default shape of the prehistoric sea in the popular imagination, and almost everything the popular imagination believes about it is slightly wrong. Let's start with what is genuinely, provably strange about these animals, because it's stranger than the myth. Every other swimming vertebrate you can name drives itself through the water with one thing. A fish drives with its tail. A whale drives with its tail. An ichthyosaur drove with its tail. A seal drives mainly with its hind flippers, a penguin with its front ones. Almost universally, aquatic vertebrates pick one propulsion system and commit to it because coordinating more than one is difficult and usually inefficient. Plesiosaurs drove with all 4 flippers, 2 at the front, 2 at the back, all 4 roughly equal in size, all 4 shaped into broad wings. And they used them not to row, exactly, but to fly underwater, sweeping them in a motion closer to the wing beat of a bird or the flight of a sea turtle than to the paddling of a duck. 4 wings beating in coordinated sequence on an animal that had no obvious modern equivalent and no clear way of working out how the 4 were timed against each other. That coordination problem has occupied scientists for decades. How do you drive a body with 4 wings without them interfering with one another, each pair churning up the water the next pair has to move through? The current best answer, from computer simulations and robotic models built specifically to test it, is elegant. The front pair leads, and the rear pair follows a beat behind, timed to catch the wake the front flippers throw off, extracting extra thrust from water that is already moving. Whether the real animals actually did this, we can't know for certain. But the whole arrangement points to a creature built not for raw top speed, but for something more valuable in a hunter: control. The ability to turn on the spot, to hover, to hold position, to accelerate in any direction. A plesiosaur was not the fastest thing in its sea. It was one of the most maneuverable. From that shared 4-winged platform, the group split into 2 very different silhouettes, and the split is worth understanding because it maps onto 2 completely different ways of being a predator. The first silhouette is the famous one: small head, enormous neck, barrel body, 4 paddles, short tail. These are the long-necked plesiosaurs, and they took the neck to lengths that are almost comic. The extreme case, from the late Cretaceous, had 76 vertebrae in its neck. 76. Its neck was longer than its body and tail combined. To give that a scale you can feel, a giraffe has 7 neck vertebrae. You have 7 neck vertebrae. Almost every mammal that has ever lived, from a mouse to a blue whale, has exactly 7. This animal had 76, stacked into a pale, tapering column 6 meters long, with a small head at the end of it. What was it for? Here is where the myth goes wrong. The old pictures show these animals holding the neck up high out of the water, swan-like, swaying, looking around. And that is almost certainly impossible. The neck vertebrae don't allow that much upward bend, and the physics of holding 6 meters of muscle and bone up in the air, cantilevered off a floating body, don't work. The plesiosaur did not raise its neck like a swan. The better explanation is about stealth, and it is far more interesting than the myth. A small head on the end of a very long neck can be eased into a school of fish while the large, alarming body stays far back, out of range, unnoticed. The fish see a small head, not much of a threat, and by the time the body's presence would matter, the head has already struck. The long neck lets a big, heavy, slow-bodied animal deliver a fast, precise, close-range attack without moving its bulk at all. It is a way of separating the dangerous part of the animal from the visible part of the animal. There is supporting evidence for how these animals fed, and it's the kind of detail that makes them real. Their fossilized stomach contents include the remains of animals that live on the seafloor, which means they were feeding downward, the long neck reaching down to the bottom while the body hovered above. And in the stomach region of many plesiosaurs, we find gastroliths, stones the animal deliberately swallowed, sometimes kilograms of them. What they were for is debated: ballast to control buoyancy, or grinding stones to help pulp food in the gut, or both. But they are unmistakable evidence of an animal doing something deliberate and strange with its own body, out there in a sea that no one would look at for 100 million years. The second silhouette went the opposite way, and it produced the true monsters of the group: short neck, enormous head, and a bite unlike anything else in the sea. These are the pliosaurs, and for much of the Jurassic, they were the apex predators of the entire ocean. The thing at the very top, the animal that ate, the animals that ate everything else. The largest well-supported specimens had skulls approaching 2 meters in length, set on bodies somewhere between 10 and 12 meters long. 2 meters of skull. The head alone was the size of a small car. The teeth matched the skull. Great conical spikes, deeply rooted, some of them with sharp cutting edges, built not to slice cleanly but to seize, to hold, and to tear a struggling animal apart. Estimates of the bite force of the largest pliosaurs put it among the very highest ever calculated for any animal. The kind of force that doesn't just kill prey, but structurally dismantles it. And they ate everything. We know this because we have their stomach contents and we have their tooth marks left in the bones of other animals. Pliosaurs ate fish. They ate squid. They ate ichthyosaurs. They ate other plesiosaurs, including, in at least one documented and slightly chilling case, a long-necked plesiosaur whose bones carry the puncture pattern of a single very large conical tooth. The animal at the top of the Jurassic Sea ate the animal we spent the first half of this chapter admiring. There is one further detail about the pliosaurs that I find genuinely remarkable because it shows an animal solving a problem in a way you would never guess. Their skulls have paired openings on the palate, on the roof of the mouth, connected to the nasal passages, arranged so that as the animal swam forward, water was drawn in through the nostrils at the front of the snout, passed over sensory tissue, and out through these palatal openings. That is not for breathing. They breathed through openings higher on the head. It is for smelling. Directionally, underwater. A separate current of water entering each nostril, letting the animal compare the two and track a scent to its source through open water, the way a shark does. Homing in on blood or on prey from far beyond the range of its eyes. Put it together, and you have one of the most formidable predators the ocean has ever built. A 10-meter animal with a 2-meter skull, a bite that could dismantle another giant, the underwater scent tracking of a shark, and the four-flippered maneuverability to turn and accelerate in any direction. For tens of millions of years, nothing in the Jurassic Sea was safe from it, and it left the tooth marks in the bones to prove it. I want to slow down here and stay with the pliosaurs for a little longer, because they raise a question that runs underneath this entire era, and it's worth asking directly. How big did the marine predators of the Mesozoic actually get, and how do we know? And how much of what we think we know is real? This matters because the sea monster is a magnet for exaggeration. Every few years, a headline announces a new, largest ever marine reptile, usually based on a single bone, usually with a length estimate at the very top of what that bone could possibly support. The truth is more careful and more interesting, and it comes down to the difference between what we have found and what we have inferred. For the largest pliosaurs, what we actually have is, in the best cases, a substantial part of a skull, and sometimes a good portion of the rest of the animal. A 2-meter skull is not an estimate. It's a measured object lying in the rock. From a skull that size, and from the proportions of more complete relatives where we have the whole body, we can estimate a total length of 10 to 12 meters with reasonable confidence. That is a real number, well supported, and it is already extraordinary. An active marine predator the length of a bus, with a head the size of a car. Where it gets shakier is at the very top of the range. There are fragments, an isolated jaw piece here, a single giant vertebra there. That hint at animals larger still, perhaps 15 meters. These fragments are real, and the animals they came from were real, and they were genuinely enormous. But a length estimate built from a single fragment carries a wide margin of error, and the honest position is that we don't yet know how big the largest pliosaurs got. We know they reached at least 10 to 12 meters. We suspect some were larger. We should be suspicious of anyone who gives a precise figure. I dwell on this because it's the difference between the way these animals are usually sold to you and the way they actually were. And the actual way is better. You don't need to inflate a pliosaur. A well-supported 10 to 12 meter animal with the strongest bite ever measured and the ability to track blood through open water is not improved by pretending it was 20 meters. The care is part of the respect. There is one more thing to understand about the bite itself, because bite force is one of those numbers that gets quoted endlessly and understood rarely. When you read that a pliosaur's bite has been estimated at some enormous figure, tens of thousands of units of force, an order of magnitude beyond a large modern crocodile, it's worth pausing on what that force was actually for. It was not, primarily, for killing. A large predator rarely needs an enormous bite to kill. A smaller, sharper bite to the right place will do it. An enormous bite force is for something else, for defeating armor and bone, for crushing through the shell of a large ammonite, or the bony head of another marine reptile, or the thick skeleton of prey too big to swallow whole. It is for taking a portion out of something that is too large, too armored, or too dangerous to deal with any other way. And that tells you something about the world these animals lived in. A bite evolved to crush bone and shell is a bite evolved for a sea full of armored, bony, dangerous prey. A sea where the medium-sized animals were not soft and defenseless, but shelled, plated, spined, and capable of fighting back. The pliosaur's monstrous bite is a fossil not just of the pliosaur, but of everything it was trying to eat. Every adaptation in a predator is a photograph of its prey. We'll come to that prey properly in a couple of chapters, because the ammonites and belemnites and armored fish of the Mesozoic are not just background. They are the foundation the whole edifice of monsters was built on, and they are strange and beautiful in their own right. But first, there is one more predator lineage to meet, and it is the one that sounds the most impossible when you say it out loud. The crocodiles that gave up the land, lost their armor, grew a fish's tail, and went to sea. Everyone knows what a crocodile is, and everyone knows what a crocodile does. It lies half submerged at the water's edge, armored, patient, waiting for something to come down to drink. It is one of the oldest and most successful body plans on the planet, essentially unchanged for a very long time, a design so well suited to ambush at the boundary of land and water that it has barely needed to evolve. So it takes a moment to absorb that during the Mesozoic, one branch of the crocodile family looked at that ancient, successful, ambush at the waterline body plan and abandoned every single part of it to become something that could not come to the waterline at all because it could no longer touch land. The metriorhynchids started, as far as we can tell, as fairly ordinary coastal crocodile relatives. Animals that hunted in shallow water and hauled out on shore, much as crocodiles do now. And then, over millions of years, they went further out to sea than any crocodilian before or since, and their bodies changed to match, piece by piece, in a way that reads almost like a checklist of everything a crocodile is, being crossed off one item at a time. The armor went first. A crocodile's back is covered in heavy, bony plates called osteoderms. Its famous armor, excellent protection on land and at the waterline. In open water, armor is dead weight, and dead weight is death for an animal that needs to move efficiently through the blue. So the metriorhynchids lost it. Their skin became smooth and bare, the only crocodile relatives ever to shed their armor entirely. The limbs went next. The legs shortened and reshaped into paddles, useless for walking, built for steering and stability in the water. The tail transformed. A normal crocodile's tail is a muscular oar, flattened side to side, that propels it with sweeping strokes. But it tapers to a point. The metriorhynchid tail developed a downward kink near its end, and from that kink hung a proper vertical tail fin, a fluke, exactly like an ichthyosaurs or a shark's. The crocodile had grown a fish's tail, and the physiology changed to match. These animals developed enlarged salt glands, allowing them to shed the excess salt that comes with living in the sea and, in effect, to drink seawater. That is the final commitment. The point at which an animal no longer needs to return to fresh water or to land at all. The result was, in effect, a crocodile that had turned itself into a small ichthyosaur, smooth-skinned, paddle-limbed, fluke-tailed, fully marine, hunting the same open-water prey. Some were slender-snouted specialists, chasing fish and squid through the water with narrow, tooth-lined jaws. And at least one was built like a pliosaur in miniature. A short, deep, powerful skull and serrated blade-like teeth. An animal that hunted large prey by removing pieces from it, a big-game hunter scaled down to a few meters. I find the metriorhynchids quietly moving, and it's worth saying why, because it gets at something true about this whole era. Here was a lineage with one of the most successful body plans in the history of land animals. The crocodile, the ultimate patient ambusher, a design that has outlasted the dinosaurs and is still with us essentially unchanged. And one branch of it threw all of that away. Gave up the armor, gave up the legs, gave up the shore, gave up fresh water, gave up the entire way of life that had made crocodiles successful, to chase a different opportunity out in the open sea, and to become something that had never existed before and would never exist again. They were not the biggest monsters in the Mesozoic ocean. They were not the most numerous, and they did not last the longest. But they are, to me, the clearest illustration of the single force that drove this entire era in the water. The sea was so full, so rich, so open at the top, that it was worth almost any transformation to get out into it. It was worth becoming a fish if you were a lizard. It was worth growing a fluke if you were a crocodile. It was worth abandoning 130 million years of adaptation to the land, over and over, in lineage after lineage, because the reward, a share of the emptiest, richest hunting ground on the planet, was worth everything it cost. And every one of those transformations was built on a foundation of prey. None of these predators could have existed without an ocean thick with things to eat. So before we reach the last and greatest of the marine reptiles, the lizards that took the whole sea in 30 million years, we need to spend some time on the animals underneath them, the shelled multitudes. the ones that filled the water in their millions and fed everything above them, and left behind so many shells that we build with their remains today. Every empire rests on something humbler than itself, and the empire of the marine reptiles rested on shells. We spend our time on the monsters because they are the monsters. The giant skulls, the dinner plate eyes, the bone-crushing bites. But a predator is only the visible top of a vast, invisible structure, and if you want to understand why the Mesozoic sea could carry so many giant hunters, you have to look down, past them, to the animals that filled the water in numbers no predator ever approached. And more than any other, that means the ammonites. If you have ever held a fossil, if there is a spiral stone on a shelf in your house, or one you picked up on a beach as a child, there is a very good chance it is an ammonite, because they are among the most abundant fossils on Earth. Coiled, ribbed, chambered, ranging from the size of a coin to the size of a car tire, they turn up in marine rock all over the world in staggering numbers. There are limestone beds in Europe where the rock surface, split open, is simply a mosaic of coiled shells packed edge to edge, thousands of them in a single slab, a frozen census of a moment in a sea 200 million years gone. They were not shells with nothing in them. Each one was the home of an animal, a soft-bodied relative of the squid and the octopus and the nautilus, living in the last and largest chamber of its coiled shell, with a ring of tentacles and a hard beak protruding from the opening. The chambers behind it were sealed and filled with gas and fluid, and by adjusting the balance between them, the animal controlled its buoyancy, rising and sinking through the water column, hovering at whatever depth it chose. It hunted small prey with its tentacles, and in turn it was hunted by nearly everything larger than itself. The ammonite was the great middle of the Mesozoic food web, abundant enough to feed the multitudes above it, and equipped, in its shell, with the only defense it had. There is a detail about ammonite shells that turns them from pretty fossils into one of the most useful objects in all of science, and it's worth understanding because it's the reason we can date the rest of this story at all. Look closely at where the internal walls of the shell, the walls between the gas chambers, meet the outer shell wall. In the earliest shelled cephalopods, that join was a simple line. But over evolutionary time, in the ammonites, it became progressively more elaborate, folding and refolding into intricate frilled patterns like the edge of a fern or the border of a snowflake. The likely reason is structural. A folded, complex join distributes stress better than a simple one, letting a thinner, lighter shell resist the crushing pressure of deeper water. But the useful consequence, for us, is that this pattern changed rapidly and distinctively over time, and it is visible on the surface of the fossil. Because ammonites evolved fast, spread across entire oceans, and then went extinct and were replaced by new forms in relatively short spans of time. A given species existed everywhere at once and only for a geological eye blink, which means that if you find a particular ammonite species in a layer of rock, you know the age of that rock. Anywhere in the world to within a fraction of 1,000,000 years. Whole chronologies of the Mesozoic are built on them. The ammonites are the clock the entire age of dinosaurs is told by. The monsters we have been describing are dated, in large part, by the shells of the animals they ate. Alongside the ammonites moved the belemnites, and they were closer to a modern squid, soft-bodied, 10-armed, torpedo-shaped, moving through the water in shoals. Their arms carried tiny hooks rather than the suckers of a modern squid, and inside their bodies they carried a hard, bullet-shaped internal skeleton that fossilizes so readily that it is very often the only trace of them that survives. Those fossil bullets litter certain Jurassic clays in such numbers that they have their own folklore. In England and across northern Europe, country people who found them long before anyone understood what they were called them thunderbolts and believed they had fallen from the sky during storms. Solidified lightning buried in the clay. They are nothing of the kind, of course. They are the internal skeletons of squid-like animals that swarmed in the Mesozoic seas in numbers beyond counting, died, and rained their hard parts onto the seafloor for 100 million years. But there is something fitting in the old name. To find one is to hold a small piece of a vanished ocean, and thunderbolt is not a bad word for that. Between the ammonites and the belemnites and the fish and the countless smaller things, the open water of the Mesozoic was not empty blue. It was thick, crowded, textured, alive at every depth. A bouillon of shelled and finned and tentacled animals so dense that it could support an entire second empire of giant predators on top of it. When you picture the sea we've been swimming through tonight, don't picture the monsters alone in clear water. Picture them moving through clouds of shells. Picture every giant hunter surrounded, always, by the drifting multitudes it fed on. The monsters are only half the ocean. The other half is the food, and the food was beautiful. And the reefs. Because there were reefs, and they were built by something that will surprise you. For part of the Mesozoic, the tropical shelves were fringed by reefs built by corals, much as they are today. But through the Cretaceous, in many places, the corals were pushed into a minor role by a completely different reef builder, a clam. Specifically, a group of bivalves called rudists that had abandoned the familiar two matching shells arrangement entirely. One of their two shells grew into a thick, heavy, conical tube, cemented upright to the seafloor, sometimes over a metre tall. The other shell shrank into a small, flat lid that sat on top like a cap. They grew in dense aggregations, tube against tube, cone against cone, until they had built genuine wave-resistant reef structures across the warm, shallow shelves. Reefs made not of coral but of clams that had turned themselves into a forest of cemented tubes. For roughly 40 million years, the primary reef-building animal on Earth was not a coral. It was a clam that had reinvented itself as a tube standing on end. It is one of the strangest facts in the history of the sea, and it is entirely characteristic of the Mesozoic, an era in which the ordinary rules kept being suspended and the familiar jobs kept being done by unfamiliar animals. There is a group we have barely mentioned that deserves its place, because it survived when the giants did not, and because it is still with us, largely unchanged, in seas all over the world tonight, the sea turtles. The turtles entered the Mesozoic Sea like everything else, a land and freshwater animal drawn into the salt water by the abundance out there. And they did something the great marine reptiles could not, or would not, do. They kept a foot on the land. A sea turtle became magnificently adapted to the water, the shell flattened and streamlined, the limbs reshaped into long paddling flippers, the whole body built for a life of open ocean cruising. But the turtles never gave up the beach. They never made the final commitment the ichthyosaurs and plesiosaurs and mosasaurs all made. They never began giving birth at sea. Instead, they did what sea turtles still do. The females returned to land to lay their eggs, hauling themselves up onto a beach with enormous effort, digging a nest in the sand, laying and dragging themselves back to the water, leaving the eggs to incubate in the warmth and the hatchlings to make their own desperate scramble to the sea. It is an ancient ritual, and it was already ancient in the Cretaceous. Some Mesozoic sea turtles were enormous. One from the inland seaway measured over 4 meters from flipper-tip to flipper-tip, one of the largest turtles that has ever existed, cruising the warm water among the mosasaurs and the ammonites. And when the end came, and the giants died, and the ammonites vanished, and the whole top of the food web collapsed, the turtles came through. Not all of them, but the lineage survived, where the specialists did not. Why? For the same reason the survivors always survive. The sea turtle was never as committed as the marine reptiles around it. It kept the beach, kept the flexibility, kept the option of the land. It was not the fastest or the largest or the most impressive animal in the Cretaceous Sea. It was a generalist that had hedged its bets, and when the catastrophe came and took the animals that had bet everything on the open water, the turtle, with its eggs safe on a beach, its diet broad, its body adaptable, simply carried on. The sea turtle you might see today, hauling up a moonlit beach to lay its eggs exactly as its ancestors did, swam alongside the mosasaurs and outlived them all. It is a living piece of the Mesozoic Sea, still doing, tonight, what it was already doing 100 million years ago. There is a question worth asking about the ammonites before we leave them, because it connects directly to how this whole world ended, and because the answer is one of the most quietly illuminating things in the fossil record. Why did the ammonites die completely at the end of the Cretaceous? Every single one, after hundreds of millions of years, when their close cousins, the nautiluses, animals of almost identical construction, came through and are still alive today? A nautilus and an ammonite are, to look at, nearly the same animal. Both are cephalopods with coiled, chambered external shells. Both control their buoyancy the same way, hang in the water the same way, carry a ring of arms and a beak the same way. They lived in the same seas, ate broadly similar things, and faced the same catastrophe. And yet the ammonites vanished utterly, and the nautiluses survived. Why? The best supported answer is about babies, and it turns out to be the whole story of the extinction in miniature. Ammonites, judging from the tiny size of the first chamber of their shells, hatched very small, under a millimetre in many cases. And a newly hatched ammonite that small could not live on the bottom or hunt for itself. It lived, at first, as part of the plankton, drifting in the sunlit surface water, feeding on other, smaller plankton. Its entire early life depended on the plankton of the surface layer being there. Nautiluses do it completely differently. They lay a small number of very large eggs, which take up to a year to develop and hatch into juveniles 2 or 3 centimeters across. Already miniature adults, already living and feeding near the bottom on carrion and slow prey, never dependent on the surface plankton at all. Now bring back the asteroid and the haze and the dying of the plankton. When the base of the surface food web collapsed, every ammonite on Earth, at every moment, had a generation of hatchlings drifting in that surface water, depending on a food supply that had just disappeared. Their nurseries were destroyed. There was no next generation, anywhere, all at once. The nautiluses, whose young had never needed the surface plankton in the first place, and who happened to make their living scavenging in deep water on exactly the kind of falling dead material that a catastrophe produces in abundance. The nautiluses simply carried on. Being smaller, slower, less diverse, less impressive, and less specialized turned out, once again, to be the winning position. The Ammonites had conquered the Mesozoic seas by the sheer efficiency of their planktonic strategy. Countless tiny young spread across the whole surface of the ocean. And that same strategy, the source of all their success, is exactly what killed every last one of them in a single dark year. The Nautilus, doing everything less impressively, is still out there tonight, rising up a reef slope in the dark off the Philippines, carrying a body plan 500 million years old through a world that ate its flashier cousins. We come now to the last and, in some ways, the most astonishing of the great marine reptiles. And to do them justice, you have to start with a fact that sounds like a mistake. The mosasaurs were lizards, not lizard-like reptiles in the loose way that everything from this era gets called a lizard. Actual lizards, squamates, the group that today contains geckos, iguanas, monitor lizards, and snakes. Their closest living relatives are probably the monitor lizards, the group that includes the Komodo dragon, or possibly the snakes. The anatomy genuinely points in both directions, and the debate is still open. But the point stands. The last great sea monster of the Mesozoic, the animal that ended up ruling every ocean on the planet, was a lizard, a cousin of the things that sun themselves on garden walls. And it happened fast. Absurdly fast. The mosasaurs first appear in the fossil record around 100 million years ago as small, unremarkable coastal animals. A meter or so long, with webbed feet, swimming in shallow water near the shore, probably still able to haul out onto land. There is nothing about these early forms to suggest what was coming. They look like what they were. Small aquatic lizards making a modest living in the shallows. Within 30 million years, their descendants were the apex predators of every ocean on Earth. Sit with how fast that is. The ichthyosaurs had taken something like 50 million years to become fully marine. The whales, much later, would need around 10 million years to become properly aquatic and another 20 to reach dominance. The mosasaurs went from ankle-deep coastal lizard to global apex predator in 30 million years. Less time than separates us from the earliest apes. It is one of the fastest large-scale takeovers of a major habitat in the entire fossil record, and they did it by rebuilding the lizard body from the ground up, at speed. Watch the rebuild happen, because every step is a solution to a problem, and together they turn a shoreline lizard into a monster. The limbs shortened, and the finger and toe bones lengthened and multiplied, packing into stiff paddles inside a webbing of soft tissue, steering surfaces, not walking legs. The body elongated and flattened from side to side, and the animal began driving itself, not with its limbs, but with side-to-side undulation of its trunk and tail, which is to say, it swam the way a snake swims, or an eel, scaled up to the size of a whale. That serpentine drive, inherited from their squamate ancestry, is part of what made them so quick to adapt. They already had a body that could be made to swim by sheer flexing, without needing to reinvent the whole propulsion system. The bones changed density, first losing it for buoyancy, and then in the largest forms regaining it in a different arrangement as ballast. And, like every fully committed marine reptile before them, they gave up the land entirely for reproduction. Mosasaur fossils have been found with unborn young inside them, and newborn mosasaurs are known from deep open ocean deposits far from any coast, which can only mean they were born at sea. The lizard that started in the shallows ended up giving birth in the open ocean, its young never touching land, never intended to. For a long time, these animals were reconstructed with a simple, straight, tapering, eel-like tail. Then, in 2008, a specimen was described that preserved not just the skeleton, but the outline of the body in mineralized soft tissue. And it showed a distinct downward bend in the tail vertebrae, supporting a large, shark-like fin. Every reconstruction since has had to be redrawn. The mosasaurs, it turned out, had independently evolved the same crescent tail as the ichthyosaurs and the sharks and, later, the whales. The fourth time, at least, that the open ocean had demanded that particular shape and been given it. But the part of a mosasaur that stays with you, once you understand it, is the mouth. A mosasaur skull has a hinge partway along the lower jaw, an actual joint in the middle of the mandible, inherited from the same snake-adjacent ancestry that gave it its swimming style. That hinge let the lower jaw flex outward, widening the gape enormously, so the animal could take prey far larger, relative to its head, than a rigid-jawed hunter could manage. And on the roof of the mouth, mounted on the palate, sat a second set of teeth, a second pair of tooth rows, angled backward toward the throat. Think about what that second set of teeth does. Prey seized by the outer teeth is held. Then the inner, palatal teeth engage and walk it backward, deeper into the throat, ratcheting it inward with no possibility of it going the other way. It is the exact mechanism a snake uses today to swallow prey whole. The same backward-pointing teeth, the same one-way ratchet, the same slow, inexorable draw toward the throat. The mosasaur was, in its feeding, a sea snake the size of a whale, and its prey, once seized, was going in one direction only. The largest species reached around 13 meters, with skulls well over 1.5 meters long. Their teeth were built as thick conical spikes rather than cutting blades, designed to seize and crush and hold rather than to slice. And we know exactly what they ate, because we have their stomach contents and the bite marks they left in the bones of other animals. Fish, sharks, seabirds, turtles, ammonites, plesiosaurs, and, routinely, each other. There are mosasaur bones bearing mosasaur tooth marks. There are mosasaur skulls with healed injuries inflicted by other mosasaurs' teeth. At the top of the last Mesozoic sea, the greatest danger to a mosasaur was another mosasaur. There is a way of feeling the mosasaur's speed of conquest that goes beyond the numbers, and it's worth trying, because 30 million years is itself a span the mind can't hold, and the achievement gets lost inside it. Here is another way to see it. When the first small coastal mosasaurs were paddling through the shallows, the seas still belonged to others, to the last of the ichthyosaurs, to the plesiosaurs, to the great fish and the sharks. The mosasaurs were nobody. Marginal little lizards in the shallows, of no consequence, the kind of animal you would not have bet on. If you had surveyed that sea and been asked which group would rule the ocean at the end of the Cretaceous, you would not have said the little coastal lizards. You would have said the plesiosaurs, or the sharks, or something already established and impressive. And then, in a span of time shorter than the gap between the first apes and us, those marginal little lizards rebuilt their entire bodies, moved out into open water, grew to the size of buses, evolved the hinged snake jaw and the double tooth rows and the shark-like tail, gave up the land, learned to give birth at sea, spread to every ocean on the planet, and took the top of the food chain away from everything that had held it before. They did not gradually rise to prominence. They erupted into it, and they did it so fast that the fossil record almost seems to skip. Small coastal animals in one set of rocks, global apex giants a few layers up. It is one of the great bursts of the fossil record, and it happened right at the end, in the last act of the Mesozoic, as if the sea had one more monster in it to produce before the curtain came down. The mosasaurs were the newest of the great marine reptiles, the last to arrive, the fastest to rise. And they had been the rulers of the ocean for only a few million years, still expanding, still diversifying, still becoming, when the sky went white and it all ended. They never got to finish. Of all the animals in this story, there is something particularly stark about the mosasaurs. They were still on their way up when the world stopped. We will never know what they would have become. There is a piece of history attached to these animals that matters more than a footnote should, and it's the right place to pause because it connects the monsters of this ocean to the whole idea we have been leaning on all night, that species can end. In the 1770s, quarry workers in a chalk mine near the town of Maastricht, in what is now the Netherlands, cut into an enormous fossil skull. It changed hands several times, was seized during a war, and eventually reached Paris, where it came under the eye of the great anatomist Georges Cuvier. Cuvier examined it and concluded that it belonged to a giant marine lizard related to nothing alive, an animal of a kind that no longer existed anywhere on Earth. That conclusion was, at the time, radical to the point of heresy. The idea that an entire kind of animal could simply cease to exist, that the world had once been full of creatures that were now utterly gone, was not yet accepted. Cuvier was among the first to argue it seriously, and he needed evidence. Real animals, clearly unlike anything living that had plainly once existed and plainly did not any longer. The Maastricht skull became one of his central exhibits. So the very concept of extinction, the idea that underlies every single thing we have talked about tonight, the idea that lets us speak of an entire vanished ocean full of vanished animals, was established in significant part through an argument about a mosasaur. The animals of this sea did not just live and die. One of them helped teach us that living things can vanish from the world completely. And within a few million years of that skull's owner swimming in a warm chalk sea, every mosasaur on Earth would do exactly that. It's worth staying with the anoxic events for a moment, because they are the quiet villain of the Mesozoic Sea. Not as famous as the asteroid, but responsible, over and over, for reshaping the ocean and clearing the way for new rulers. Several times during this era, and especially through the Cretaceous, the deep ocean simply ran out of oxygen. These are the ocean anoxic events, and they are recorded all over the world as distinctive black bands in marine rock, dark, organic-rich layers that form when the deep water goes stagnant and the bottom fills with undecayed matter because there is no oxygen down there to rot it. Why did it happen? The Mesozoic was a warm world, and warm water is the root of the problem for two reasons that compound each other. First, warm water simply holds less dissolved oxygen than cold water. The same reason a warm, fizzy drink goes flat faster than a cold one. And second, the modern ocean's oxygen supply to the deep depends on cold, dense water sinking at the poles and carrying oxygen down with it, driving a global circulation that keeps the deep sea ventilated. In a warm world with no polar ice and little cold deep water formation, that circulation weakens. The ocean stratifies into layers that stop mixing. The surface stays oxygenated. The deep goes still and stagnant and eventually dead. Add to that the occasional pulse of large-scale undersea volcanism, which warmed the planet further and fertilized the surface water with iron and nutrients, triggering enormous blooms of life that then died and sank and rotted, stripping still more oxygen from the water below. And you get the recipe for a periodic catastrophe. The worst of these Cretaceous events, around 94 million years ago, killed a significant fraction of marine life and reshaped the ocean's inhabitants. These events are the reason the ichthyosaurs faded when they did. They are part of why the cast of the Mesozoic sea kept turning over, one group of rulers giving way to another. And they carry a warning that is not lost on anyone studying them now, because the mechanism, a warming world, a stratifying ocean, a deep sea losing its oxygen, is not purely a thing of the deep past. The Mesozoic ran the experiment many times of what happens to a warm ocean's oxygen. The results are written in those black bands in the rock, and they are worth reading carefully. But for the animals of the time, the anoxic events were simply part of the rhythm of their world, a periodic darkening and emptying of the deep, a reshuffling of who ruled what, another turn of the long wheel that had been turning since the sea first filled with life. They did not know they were living through an event. They only knew, if they knew anything, that some seas were good and some were bad, and that the good ones were very good indeed. Let me tell you how these fossils actually come to us, because the story of their discovery is bound up with the story of the animals, and it changes how you hold the bones. For most of human history, no one knew these animals had ever existed. Their fossils turned up. They always had. But they were understood as the bones of dragons, or of giants, or of animals drowned in the biblical flood, or simply as strange stones. The idea that they were the remains of real creatures that had lived in real seas unimaginably long ago and then vanished from the world entirely is surprisingly recent. It had to be invented, and the marine reptiles were central to inventing it. Much of that invention happened on one stretch of crumbling coast in the south of England in the early 19th century, and much of it happened through the hands of one remarkable person who received, for most of her life, almost none of the credit. She was born in a seaside town in 1799, the daughter of a cabinet maker who supplemented his income by selling curious fossils to tourists. She began collecting as a child, learned the cliffs and their dangers intimately, and had almost no formal education. As a working-class woman in the England of her time, she could not join the scientific societies, could not publish under her own name, could not receive credit in the papers written about the things she found. And what she found was extraordinary. As a girl, she uncovered one of the first ichthyosaur skeletons ever recognized for what it was. She found the first complete plesiosaur, a specimen so strange that a leading anatomist in France initially declared it must be a fake, a real neck attached to a different animal's body, before conceding it was genuine. She understood the geology of her cliffs better than most of the gentlemen who bought from her, worked out what the animals had eaten from their fossilized gut contents, and supplied the raw material for a great deal of the early science of these seas. She worked in physical danger. The same cliffs that gave up the fossils regularly collapsed, and she nearly died in one landslip that killed her dog. And she worked in relative poverty, and she died of cancer at 47. The specimens she pulled from that coast are in museums today, and a great deal of what we understand about the marine reptiles rests, ultimately, on what her hands lifted out of the blue-gray rock. I mention her because it matters that these animals did not simply appear in our knowledge. Somebody found them, often at real cost, sometimes without recognition, and pieced them together and worked out what they were, and in doing so helped establish the almost unbelievable idea at the center of everything we've said tonight, that the world was once full of creatures utterly unlike anything alive that lived and ruled and then vanished completely. The monsters are real. But so are the people who dug them out of the cliffs and taught us how to see them, and the two stories belong together. I want to take you to one specific sea now, and stay in it for a while, because it has been studied more completely than almost any other body of water that no longer exists, and because standing in one real place is worth more than 100 generalizations. For most of the late Cretaceous, North America was not one continent, but two, split down the middle by a warm, shallow sea that ran all the way from the Gulf of Mexico in the south to the Arctic Ocean in the north. It was around 1,000 kilometers across at its widest, and rarely more than a few hundred meters deep. A vast, shallow, muddy sea lying over the middle of a continent, warm and green and teeming. It is called the Western Interior Seaway, and its floor is now the dry land of Kansas, Nebraska, the Dakotas, and the plains of central Canada. We know this sea unusually well, and the reason is a happy accident of how it preserved things. The seaway was shallow, and its bottom water was frequently low in oxygen, which is bad for living in but wonderful for fossilization, because a carcass that sinks into oxygen-poor mud is not torn apart by scavengers or churned up by burrowers. It is covered gently by fine sediment and left. So the seaway preserved its dead with extraordinary completeness. Whole articulated skeletons, stomach contents still in place, skin impressions, and sometimes entire community snapshots. A predator fossilized with its last meal inside it, an animal preserved in the act of dying. Which means we can describe this one vanished sea with something close to the confidence of a modern nature survey. So let's descend into it, from the surface down, and meet the whole community at once. At the surface, the light comes down warm and green through slightly turbid water, thick with the drifting white specks of countless microscopic plankton. Small fish shoal in the bright upper layer in their thousands. And above the water, skimming the surface on the sea breeze, are pterosaurs, flying reptiles with wingspans of 6 or 7 meters, gliding low over the waves and dipping to snatch fish from the top meter of water. They are not part of the sea, exactly, but they live off it, patrolling its ceiling. It's worth dwelling on the pterosaurs a little, because they belong to this story more than people realize. Not as sea creatures, but as the ceiling of the sea, the layer of danger that came from above. The pterosaurs were flying reptiles, not birds and not dinosaurs, a separate lineage that had conquered the air tens of millions of years before the first bird. And the largest of the coastal and marine-going pterosaurs were enormous, wingspans of 6 or 7 meters in the ones that patrolled the Cretaceous seaways, and in some later forms far larger still. They soared over the water on the sea breeze, riding the air the way an albatross does, covering great distances with little effort, and they dropped to the surface to take fish from the top layer of the sea. For a fish near the surface, or a squid, or an ammonite hanging just below the waves, the pterosaurs were the danger from above, a threat that came out of the sky, the way the mosasaurs came out of the deep. The surface of the Mesozoic Sea was a boundary with hunters pressing in from both sides, reptiles below reaching up, reptiles above reaching down. To live near the surface was to be caught between two kinds of death, one rising from the dark water and one falling from the bright air. There is something complete about that image, and it's worth carrying. The Mesozoic ocean was not a flat world with predators only within it. It was a three-dimensional world with pressure from every direction. The deep divers coming up from below, the pursuit hunters ranging through the middle water, the great reptiles cruising the surface, and the pterosaurs soaring above, dropping down through the ceiling to feed. From the seafloor to the sky, the whole vertical column was a hunting ground, layered with danger at every level. A small fish in that sea lived its whole life inside a shooting gallery that extended from the mud below to the clouds above, and the only safety was in numbers and in never being the one the shadow chose. Just below the surface swim the diving birds, and these are strange and worth pausing on. They are birds, descendants of the same lineage that produced everything with feathers today, but they are flightless in the air and superb underwater. Their wings are reduced, their legs set far back on the body for propulsion, and this is the detail that marks how deep in time we are. They still have teeth in their beaks, small, sharp teeth for gripping fish. Toothed, flightless, diving seabirds, chasing fish through the upper water like the loons and cormorants that would come much later, but with a mouthful of teeth no modern bird possesses. They come ashore only to breed and are nearly helpless on land and spend their lives in the water hunting. It's worth pausing on the diving birds a little longer, because they are one of the most revealing animals in this whole sea, and they connect the Mesozoic ocean to a world we know. A bird with teeth sounds like a contradiction, but it is only a contradiction because every bird alive today happens to lack them. In the Cretaceous, teeth in a bird's beak were normal. These diving birds were part of an early branch of the bird family tree, descendants of small, feathered dinosaurs, true birds by any reasonable definition, but retaining the toothed jaws of their ancestors, which their modern relatives would later lose. What makes them worth pausing on is what they were doing. Here was a bird, an animal built, at its origin, for flight, for the air, the most aerial group of vertebrates that has ever existed, going the same way as all the reptiles around it, back down into the water. The wings that its ancestors had evolved for flight were reduced, nearly useless in the air, reshaped for propulsion underwater. The legs were set far back on the body for swimming, so far back that on land the animal could barely stand. It had become a diving, swimming, fish-hunting seabird that had largely given up the sky in a sea already full of reptiles that had given up the land. Think about what that means. In the same warm Cretaceous sea, at the same time, you had lizards that had become fish-shaped monsters, crocodiles that had grown flukes, and birds that had abandoned flight to dive. Three completely different kinds of land and air animal, all independently drawn down into the same rich water, all rebuilding their bodies away from their origins to exploit the same abundance. The sea was so full, so rewarding, that it pulled animals into it from every direction, from the land, from the shore, and even from the sky. Everything that could find a way into that water did, and paid whatever it cost in lost wings or lost legs or lost armor, because the reward was a share of the richest ocean the world had known. The toothed diving birds died with everything else at the end of the Cretaceous. The birds that survived, the ancestors of every bird alive today, were mostly the flying ones, the ones that had kept the sky. But for a while, in that warm sea, there were birds with teeth chasing fish underwater alongside the mosasaurs, and it is one of the small, strange wonders of a strange and wonderful ocean. In the middle water drift the ammonites, in enormous variety, from tight coiled discs the size of a hand to strange, straightened, uncoiled forms, some of them 2 meters long, hanging vertically in the water column like floating spears. Shoals of squid-like animals move through them, and through it all move the fish, including one predatory giant 5 or 6 meters long, with a heavy body and a bulldog jaw full of fangs several centimeters long. That fish deserves its own moment because of a single fossil. There is a specimen, probably the most famous fossil fish in the world, in which one of these giants, around 4 meters long, swallowed another fish nearly 2 meters long, whole, head first. And then it died immediately, apparently because the prey was too large and was still struggling and ruptured something on the way down. The two are fossilized together, one inside the other, the smaller skeleton nested perfectly within the larger, preserved in the exact posture of a fatal mistake. A fish that died of ambition 90 million years ago and held that shape for us to find. There is no better single illustration of what this sea was. A place where everything was eating, everything, constantly, and where the eating sometimes killed the eater. Deeper, above the muddy bottom, cruised the sharks. At least a dozen kinds, from small bottom dwellers with crushing teeth for eating shellfish up to a large pursuit predator, 7 meters long, with serrated triangular blades for teeth. That big shark is known well enough that we have specimens with its last meal preserved inside it, and specimens showing the marks of what fed on it in turn. It hunted the mosasaurs, the plesiosaurs, the large fish, the diving birds. There is a famous plesiosaur skeleton with a set of this shark's teeth still embedded in its bones, the record of a specific hunt, a specific death in this specific sea. It is worth spending a moment on the sharks of this sea, because they are the one group of large predators that ran through the entire Mesozoic and out the other side, and their survival, next to the reptiles' extinction, tells you something. Sharks were already ancient when the Mesozoic began, a lineage hundreds of millions of years old, having already survived catastrophes that ended other groups entirely. Through the age of the marine reptiles, they were never the dominant predators. That role belonged to the pliosaurs and the mosasaurs and the great fish. But they were always there, in the background, at every size and in many forms. Small, bottom dwellers with crushing teeth for shellfish, midwater hunters, and large pursuit predators several meters long with serrated blade teeth, capable of taking on the marine reptiles themselves. And crucially, it was during the Mesozoic that the modern sharks emerged. The sharks of the earlier eras had been somewhat different animals. It was in the Jurassic and Cretaceous that the lineages leading to today's sharks appeared, with their fast-replacing teeth and their flexible, protrusible jaws. The body plan that every shark alive tonight still carries. They were small and unremarkable at the time, overshadowed by the reptilian giants. But they were quietly perfecting the design that would carry them through the coming catastrophe and into the modern ocean. When the asteroid fell and the great marine reptiles died, the sharks were hit. Many lineages, especially the specialized open ocean hunters, disappeared. But the group survived, as it had survived everything before. And in the emptied sea that followed, with the reptilian apex predators gone, the sharks were among the animals that inherited the top. Every shark in the ocean tonight is a survivor of that ending, a descendant of the modest Mesozoic sharks that lived in the shadow of the mosasaurs and outlasted them all. There is a pattern here that we keep meeting, and it is worth naming one final time. The sharks did not survive because they were the biggest or the fiercest or the best adapted to the Mesozoic sea. They survived because they were flexible, ancient, tolerant, and never overcommitted to any single vanishing set of conditions. The reptiles that ruled the sea are gone. The sharks that lurked beneath them are still here. The meek, once again, inherited the water. And the sharks, for all their teeth, were in the relevant sense the meek, the adaptable, the enduring, the ones who never bet everything on a world that could end. On the bottom itself lay enormous flat clams, some more than a meter across, resting in dense beds on the mud. Small fish sheltered inside their open shells. And we know this extraordinarily, because sometimes those small fish are fossilized in there, having taken refuge in a giant clam and been buried with it. Oysters encrusted every hard surface. Free-swimming crinoids, relatives of starfish, drifting rather than anchored, moved through the water above. And moving through all of it, at the top of everything, were the mosasaurs. 5 or 6 different kinds present at any one time, from 3-meter coastal forms up to the 13-meter open water giants, cruising the whole sea from surface to floor, eating the fish and the birds and the ammonites and the plesiosaurs and one another. The entire structure, every animal I have just named, from the plankton to the giant mosasaur, was ultimately built on the reign of microscopic plankton at the surface. Those single-celled algae bloomed in the warm, sunlit upper water, lived, died, and sank, their tiny armored plates drifting down onto the seafloor at a rate that built the chalk beds of the American plains at something like a centimeter every 1,000 years. Everything in that sea was, at bottom, eating sunlight, processed through plankton, passed up through shells and fins and jaws to the giant lizards at the top. It was a complete world, layered from surface to floor, balanced, full, and running smoothly, exactly as it had run for millions of years. And every single animal I have just described, Every genus in this entire chapter was gone within a geological instant of the end of the period. Not reduced, not restructured. Gone, along with the sea itself, which drained away as the continent rose and the waters fell. If you drive across Kansas today, across the flat wheat country in the middle of the continent, you are driving on the floor of it. The sea is gone, but its bottom is still there, holding the fish that died of ambition and the plesiosaur with the shark's teeth in its bones, a few meters beneath the road. We have met the animals. Now I want to spend a while on how they actually lived. Not the anatomy, but the days. How they were born, how they moved, how they hunted, how they died. Because a catalog of monsters is not the same as an ocean, and it's the living that makes a world. Start with birth, because it is the most extraordinary thing about these animals, and the one we have the best evidence for. Every one of the fully marine reptiles, the ichthyosaurs, the mosasaurs, the plesiosaurs, gave birth to live young in the open water. None of them laid eggs. None of them could. And this changes everything about how you should picture their lives, because it means the entire life cycle, from birth to death, happened in the sea. There was no beach, no nest, no shore. A baby ichthyosaur's first experience of the world was open blue water, its mother beside it, the surface far above and the dark far below. It had to swim immediately. It had to breathe immediately, rising to the surface for its first breath within moments of birth. There was no gentle land-based infancy, only the water and the need to function in it from the first minute. We can say something about the young themselves, too. Some plesiosaur fossils suggest these animals gave birth to a single, very large baby rather than a litter of small ones, which is significant because that is the reproductive pattern of animals that care for their young. A creature that produces many small offspring generally abandons them to their fate. A creature that produces one large, well-developed offspring at a time is often one that invests in it, protects it, keeps it close. It is at least possible, not proven, but possible, that some of these giant marine reptiles lived in social groups and cared for their young, the way whales and dolphins do now. That the long-necked plesiosaur cruising the Cretaceous Sea was not always alone, but moved with its family, its single large calf swimming in the slipstream beside it. We cannot see that directly, but the shape of the evidence points at it, and it is worth letting yourself imagine. These were not always solitary monsters in an empty sea. Some of them, at least, may have had company, may have had young that they knew and stayed near and defended. Now the hunting, because the different body plans we've met were different answers to the same question. How do you catch food in the open sea? And each answer implies a completely different kind of day. The ichthyosaur's day was vertical, built for deep diving, with those enormous light-gathering eyes. It spent its hunting hours descending, down through the sunlit surface, down past the point where the light goes blue, down into the twilight zone hundreds of meters deep where squid and fish move in near darkness. It hunted by sight, in conditions where almost nothing else could see, seized its prey, and rose again to breathe. Down into the dark, up into the light, over and over, all day and through the night. Its life was a slow vertical rhythm between two worlds, the breathing world above and the hunting world below, tethered forever to the surface by its need for air but making its living in the deep. The plesiosaurs' day was patient. The long-necked forms were not built for pursuit. They were built for stealth and precision. Picture one hanging almost motionless in the middle water, its huge body still, its four flippers making tiny adjustments, its long neck extended and creeping. The small head easing toward a school of fish while the body stayed far back and unnoticed. A slow, careful, deliberate hunter, spending its energy not on chasing but on positioning, waiting for the geometry to be right and then striking with just the head while the body never moved at all. The pliosaur's day was dominion. At the top of the Jurassic food web, tracking prey by scent through open water, it did not need stealth or patience in the same way. It cruised, and it smelled, and when it found something, a fish, an ichthyosaur, another plesiosaur, it ran it down and took it apart. Its day was the day of the thing nothing else hunts, moving through its sea with the particular unhurried confidence of an animal that has nothing to fear from anything it will meet. And the mosasaur's day, at the very end of the era, was ambush and pursuit combined. A fast, flexible, snake-bodied hunter that could accelerate out of nowhere, seize prey in a gape widened by its hinged jaw, and ratchet it inexorably down its throat. In the last Cretaceous seas, the mosasaur's day was mostly about other mosasaurs, competing with them, avoiding the larger ones, and, when the opportunity came, eating the smaller ones. It's worth asking what these animals were warm or cold, whether they were cold-blooded, like the reptiles they descended from, or whether they had found some way to run hot, like the mammals and birds. Because the answer, as far as we can tell, is stranger and more interesting than a simple yes or no, and it changes how you should picture them. A modern reptile is ectothermic. It takes its body temperature from its surroundings, basking to warm up, seeking shade to cool down. That works well enough on land, in the sun. But it works badly in the open ocean, and especially badly in cold or deep water, because water pulls heat out of a body far faster than air does, and there is no sun to bask in 300 meters down. An animal that hunted in the cold deep, or that ranged from the tropics to the cool high-latitude seas, or that needed sustained power for long-distance swimming, could not afford to have its body temperature simply follow the water. And the evidence suggests that at least some of these marine reptiles didn't. Chemical analysis of the fossils, the isotopes locked into their teeth and bones, which record the temperature at which the animal's body operated, suggests that ichthyosaurs and plesiosaurs maintained body temperatures well above the surrounding water, warm and relatively stable, regardless of how cold the sea around them was. They had found some way, like modern tuna and some sharks, to generate and retain heat, to run their bodies hot in cold water. This matters because it changes the animal in your mind. A warm-bodied ichthyosaur is not a sluggish, cold-blooded thing waiting for the sun. It is an active, powerful, high-performance hunter, capable of sustained speed and deep cold dives, its body humming with generated heat in the blue-black dark. Far closer, in its physiology and its lifestyle, to a dolphin or a tuna than to any lizard sunning itself on a rock. The convergence we keep returning to, the way these reptiles came to resemble mammals and fast fish in body shape, ran deeper than shape. It reached into their physiology, their metabolism, the very warmth of their blood. They were reptiles by ancestry, But out in the open sea, doing a mammal's job, many of them had quietly become something a lizard would not recognize. Warm-bodied, high-powered, deep-diving hunters running hot in a cold ocean, as far from a basking lizard as it is possible for a reptile to get. I want to add one more predator to the role, because it is easy to forget among the reptiles, and because it shows that the giant hunters of this sea were not only reptilian. The large predatory fish of the Cretaceous were, in their own right, monsters. We met one already in the inland sea. The 5 or 6 metre bulldog-jawed giant, the one preserved with a 2 metre fish swallowed whole inside it. But it was not alone. The Mesozoic seas held predatory fish of real size and power, some of them among the largest bony fish that have ever lived, hunting the same shoals and the same open water as the reptiles. These fish matter because they remind us that the sea was not simply divided between reptiles at the top and shellfish at the bottom. It was a full, complex, many-layered food web with predators of several completely different kinds. Reptiles, fish, sharks, overlapping and competing at the larger sizes. A big predatory fish might be prey to a mosasaur and predator to a smaller reptile in the same afternoon. The neat pyramid we draw, with one apex predator at the top, is always a simplification. The real sea was a tangle, with many large hunters of many different ancestries all working the same rich water, eating each other's prey and sometimes each other. And the largest of these fish were fast, built for pursuit, with powerful tails and streamlined bodies, capable of running down prey in open water. In a sea where the reptilian giants were often ambushers or patient stalkers or deep divers, the great predatory fish occupied the role of the fast open water chaser, the pursuit hunter, adding yet another kind of danger to an already dangerous ocean. When you picture the midwater of the Cretaceous Sea, don't picture the reptiles alone. Picture the great fish among them, hunting the same shoals, as large and as formidable in their way as anything with lungs. I want to end this chapter on the deep, because it is where we began tonight, with the dinner plate eye hanging motionless in the dark, and because the deep is the part of this ocean that most resists our looking. For the whole of the Mesozoic, the deep open water was the domain of the ichthyosaurs, and then, after they faded, it was hunted by whatever could reach it. It was a world of almost no light, of cold rising up from below, of prey that had to be found by the faintest available cues. And it is the part of this vanished ocean we can say the least about, because the deep sea fossilizes poorly and gives up its secrets slowly. We know these animals went down there. We know they hunted there. We know it from the size of their eyes and the damage in their bones. But what those dives were actually like, what an ichthyosaur experienced, 400 metres down in a Jurassic midnight, closing on the glimmer of a squid, is beyond us. It happened in full, every day, for tens of millions of years, and no eye that could record it was ever present. There is something in that worth holding as you drift tonight. This entire ocean, layered, teeming, monstrous, complete, ran its full course without a single witness. Every hunt, every birth, every death in the dark happened in complete detail and was seen by nothing that could remember it. It was not a story while it was happening. It became a story only now, only tonight, only because we came along 100 million years too late and pieced it together from shells and bones and the marks of teeth. The animals did not need us to watch. They never knew they would one day be watched. They simply lived in the warm, silent sea until the morning it ended. Let me say something about scale before we go on, because these animals are usually described with numbers. 13 meters, 2-meter skull, dinner plate eye, and numbers slide off the mind without leaving an impression. It's worth translating a few of them into things the body can feel. A large mosasaur was around 13 meters long. Picture a city bus, the long articulated kind, and then picture it as a single living animal, flexing from end to end, driving itself through the water with a snake's undulation, 1.5 meters of jaws at the front. That is one animal, and it was not rare, not a freak. There were several kinds of animal that size in the same sea at the same time, cruising the same water, competing with and eating one another. A large pliosaur's skull approached 2 meters. Stand a tall person against a wall and mark their height. The pliosaur's head, from the tip of the snout to the back of the skull, was longer than that. The head alone. Now add a body 10 to 12 meters behind it. The whole animal was the length of a large truck, and the head was the size of a small car, and it could track blood through open water and crush bone with the strongest bite ever measured. The ichthyosaur's eye was 23 centimeters across, the size of a dinner plate, as I keep saying, because it is genuinely the most useful comparison. Hold up a dinner plate and look at it. That was one eye. The animal had two, set into a streamlined head, gathering light in the blue-black deep. They were among the most extraordinary sensory organs the vertebrate world has ever produced, and they were staring into a darkness we will never see. And the ammonites, the largest of them, reached nearly 2 meters across the coil. Picture a shell taller than a person, spiraled, ribbed, drifting in the open water with a ring of tentacles and a beak protruding from its opening. That is not the little spiral stone on your shelf. That is its largest cousin, a shelled animal the size of a small car hanging in a Cretaceous sea. I give you these not to overwhelm, but to make them real, because the danger with a documentary like this is that the animals become a parade of statistics, and statistics do not disturb sleep or fill dreams. These were not numbers. They were enormous living bodies, warm-blooded or cold, breathing air, giving birth, hunting and fleeing and dying in a real sea that you could have swum in had you been born 100 million years too early and been very brave and very foolish. The scale is not a fact about them. It is the first thing you would have felt looking up as the shadow passed overhead. For 180 million years the empire held. Through the Triassic, the Jurassic, and the long Cretaceous, the marine reptiles ruled the seas of this planet without serious challenge. The cast changed. The ichthyosaurs faded, the mosasaurs rose, but the empire itself never fell. The sea belonged, from the surface to the deep, to air-breathing reptiles that had come down from the land and made the water their own. And at the end of the Cretaceous, none of it was in decline. This is the thing that has to be understood about the ending, because it is the opposite of what you might expect. There is no signal in the rock in the last 1,000,000 years of the Cretaceous of a sea in trouble. The ammonites were diverse and abundant. The mosasaurs were still diversifying, still producing new forms, still increasing in size. The plankton was blooming. the chalk was accumulating. The whole layered structure from surface to floor was running exactly as it had run for tens of millions of years. If you had lowered yourself into that sea on the last morning, you would have seen an ocean at the height of its powers, full to the brim, with no hint of an ending anywhere in it. Before the ending, I want to give you one more scene from the living sea. A single ordinary day in the middle of the Cretaceous, reconstructed as faithfully as the evidence allows, so that you have one complete picture to carry down into sleep rather than a catalogue of parts. It is warm everywhere, from the surface to as deep as the light reaches. The water is a clear blue-green near the top, fading to blue, then to blue-black in the deep. It is nearly silent. No whale song, no dolphin clicks, none of the deliberate sound the ocean would fill with later. Just the vast, slow movement of water and the faint sounds of bodies moving through it. Near the surface, in the bright layer, the plankton drift in their countless billions, and the small fish move through them in shoals that turn and flash as one. Ammonites hang in the mid-water, ribbed and coiled, adjusting their depth, tentacles trailing, drifting through clouds of their own smaller kin. A shoal of belemnites jets past, 10-armed and quick. Above the surface, a pterosaur tilts on the breeze and dips to take a fish. Below, a toothed diving bird arrows down through the bright water after another. Deeper, an ichthyosaur descends into the twilight, its huge eyes wide, its warm body driving it down into the cold on a hunting dive that will end hundreds of meters below in the near dark, closing on a squid. A long-necked plesiosaur hangs almost motionless in the middle water, its four wings barely moving, its small head easing forward on that impossible neck toward a school of fish that has not yet understood the danger. And through all of it, unhurried, a great mosasaur cruises. 13 meters of flexing, snake-bodied lizard, its shark-like tail sweeping slow, and even its hinged jaws closed, its eye taking in the shoals and the shells and the smaller hunters, choosing in no hurry, because nothing in this sea is a threat to it except another of its own kind. None of them knows anything is coming. None of them ever will. The plankton bloom, the ammonites drift, the ichthyosaur dives, the plesiosaur stalks, the mosasaur cruises, exactly as they have every day for millions of years, exactly as they will tomorrow, and the day after, and for what should be millions of years more. The sea is full and warm and balanced and silent, running its long, smooth course under a sky that shows no sign of anything at all. Hold that picture. That is the ocean at its height, the last great age of the marine reptiles on an ordinary afternoon, with everything in its place and nothing wrong. Everything that comes next takes it all away. But right now, in this scene, it is all still here, all still moving, all still alive. Let that be the sea you carry down into sleep. Not the ending, but this. The warm, full, silent ocean at the height of its long afternoon, with the great shapes moving through it, unaware and unafraid. Before we leave the living sea for its ending, hold one more time the strangeness of what we have been describing, because familiarity dulls it, and it deserves to stay sharp. We have spent this time describing an entire, complete, functioning ocean. An ocean with everything ours has. A deep-diving hunter of squid like our sperm whale. A fast, open-water pursuit predator like our tuna and sharks. A patient ambusher. A shellfish crusher. A filter of small prey. Reef builders on the shelves. Vast shoals of mid-water prey. An apex giant at the very top. Every ecological role our ocean has, that ocean had too. It was, functionally, a complete and recognizable sea, and almost nothing in it was related to anything in ours. The deep diver was a reptile, not a whale. The pursuit predators were reptiles and fish, not dolphins. The apex giant was a lizard, not an orca or a great white. The reef builders were clams, not corals. The dominant mid-water prey were ammonites, shelled cephalopods that have no close living equivalent at all. It was a complete ocean, running all the same machinery as ours, staffed almost entirely by animals from other branches of the tree of life, solving the same problems in unfamiliar bodies. This is the thing that makes the Mesozoic Sea worth a whole night of attention. It is not just a collection of extinct monsters. It is proof of something profound about how life works. That when you have a rich ocean with a certain set of roles to fill, life will fill them again and again with whatever raw material is available. Give it lizards, and it will make a lizard into the shape of a shark. Give it crocodiles, and it will grow one a fluke. Give it reptiles where we have mammals, and it will build, out of that completely different starting material, an ocean that works exactly like ours and looks like nothing we have ever seen. The roles are eternal. The occupants are temporary and interchangeable, and drawn from whatever happens to be lying around when the sea has an opening. Our ocean, with its whales and dolphins and sharks, is just the current cast. The Mesozoic Sea was an earlier cast, in the same play, and one day there will be another, made of animals we cannot imagine, filling the same roles in bodies we would not recognize. The sea goes on. Only the actors change. And then, on an ordinary morning, the sky in the western sky went white. The object was somewhere in the region of 10 to 15 kilometers across, and it struck the shallow sea off the coast of what is now the Yucatan Peninsula in the Gulf of Mexico. What happened in the first hours was violent and regional. Waves higher than any in recorded history radiating out across the Gulf and beyond, a pulse of heat, a rain of molten rock droplets falling back out of the sky across half the world within about half an hour of the impact. But the waves and the heat killed regionally. What killed the ocean globally was slower and quieter, and it began at the very bottom of the food web. The impact site happened to be rich in sulfur-bearing rock, and the impact threw an enormous quantity of that sulfur into the upper atmosphere, where it formed a fine, highly reflective haze that spread around the planet and stayed for years. That haze blocked the sun. Sunlight reaching the surface fell dramatically, by most estimates, catastrophically, for a period of years. And in the ocean, sunlight is not a luxury. It is the entire foundation. Everything in that sea, from the smallest drifting speck to the 13-meter mosasaur at the top, was ultimately eating sunlight, captured by the plankton and passed upward. Shut off the light, and the plankton dies within weeks. And when the plankton dies, the entire structure above it, every animal in this whole program, begins to starve from the bottom up. That is exactly what the record shows. The plankton at the base, the tiny armored algae that had been building the chalk, and their single-celled companions, suffered one of the most complete extinctions of any group in the history of life, essentially overnight in geological terms. And with the base gone, everything that depended on it followed. Here is the casualty list. It is the end of almost everything we have spent tonight with. The mosasaurs, every species, worldwide, gone. 30 million years from coastal lizard to global apex predator, and then, in a geological instant, nothing. The plesiosaurs. After more than 130 million years, the entire lineage, the long-necked rowers and the short-necked giants alike, ended. The ammonites, gone. All of them. After hundreds of millions of years, after filling every Mesozoic sea in their countless millions, after serving as the clock we tell the whole era by, not a single one survived. The belemnites, gone. The rudists, the clams that had built the reefs, gone, and their reefs with them. The great toothed diving birds, gone. The giant predatory fish, gone. The whole layered world of the western interior seaway. The pterosaurs at the surface, the toothed birds, the shoaling ammonites, the fish that died of ambition, the sharks, the giant clams, the mosasaurs at the top. Gone, all of it, along with the sea itself. The empire that had held for 180 million years, that showed no sign of weakness on its last morning, ended inside a span of time too short to see in the rock. Not because it was failing, not because something better had come along, but because a rock fell out of the sky in exactly the wrong place, and the light went out, and the plankton died, and an ocean built on sunlight cannot survive the dark. And then the sea was quiet in a way it had not been for 180 million years. Not the living quiet of the Mesozoic, the warm, full, near-silent ocean we set out into at the start of tonight. This was a different quiet, an emptied one. For the first time in a very long time, there were no large air-breathing predators anywhere in the water. The niche at the top, the deep diver, the pursuit hunter, the apex giant, all the roles the reptiles had filled for so long, stood vacant again, exactly as it had stood vacant at the very start of the Mesozoic, before the first lizard walked down the beach into the empty sea. And the sea would stay that way, more or less, for something like 10 million years. A long, quiet, emptied stretch, the water rebuilding its plankton, its fish, its shells, slowly from the survivors. The small, the tolerant, the unspecialized, the ones that could ride out a catastrophe on almost nothing. And then, as it always does, the land noticed the empty water, and something came down to the edge of the sea to feed, and stayed, and began, over tens of millions of years, to rebuild itself around swimming, exactly as the reptiles had done at the start of the Mesozoic. But it was not a reptile this time. It was a small, four-legged, hoofed mammal, standing in the shallows of a warm sea, hunting fish. And its descendants would become the whales. And the whales would fill the empty ocean with something the Mesozoic sea never had: sound, song. The deep water full of voices, carrying for hundreds of kilometers in the dark. But that is a different story for a different night. Tonight belongs to the reptiles and their long, warm, silent empire, and its ending. Let me put the whole shape of it down one more time, and then we'll stop. There was a warm sea, with no ice at either pole and no voice anywhere in it, and it lasted 180 million years. Into that sea, over and over, animals came down from the land and gave up everything to live in it. A lizard became a fish, with eyes the size of dinner plates, and went down into the dark to hunt. Another lineage grew 4 wings and learned to fly underwater, and split into the long-necked stalkers and the short-necked giants with the bone-crushing bite. A crocodile shed its armor and grew a fish's tail and swam out past the sight of land. And at the very end, a small coastal lizard rebuilt itself in only 30 million years into the ruler of every ocean on Earth. Beneath them all, the water was thick with shells. The coiled ammonites in their countless millions, the squid-like belemnites that country people once called thunderbolts, the clams that turned themselves into reefs, and everything, from the smallest plankton to the largest mosasaur, was built on sunlight falling through warm, shallow water onto a sea that covered half the drowned continents of the world. It was complete. It was balanced. It was full. It gave birth to its young in the open water and hunted in the deep dark and ran its whole vast course every day for 180 million years without a single witness. And then a rock fell out of the sky in the wrong place, and the light went out, and the plankton died, and the whole empire, not failing, not declining, at the very height of its powers, ended in a single morning. The mosasaurs, the plesiosaurs, the ammonites, all of it, gone. The sea went quiet and stayed quiet and waited for something new. None of it planned, none of it building toward anything. Just warm water and sunlight and 180 million years of enormous animals living enormous lives that no one would ever see. And then an ending that no one could have prevented, and a long silence, and, eventually, something new coming down to the water to begin again. I keep returning to one idea tonight, and I want to state it plainly before we reach the end, because it is the deepest thing this ocean has to teach, and it is easy to miss inside the parade of monsters. Everything in this sea was temporary, and nothing in it knew that. The ichthyosaurs ruled the deep for over 100 million years, and then faded, and did not know they were fading. The pliosaurs sat at the top of the Jurassic, and did not know the Jurassic would end. The ammonites filled every sea for the entire era, and did not know that a single dark year would take every last one of them. The mosasaurs rose to rule everything in 30 million years, and did not know they had only a few million years to enjoy it. Not one animal in this entire story had any sense that it belonged to an age, or that the age would close, or that it was part of anything larger than its own single life in the warm water. And yet the ages did close, one after another, and the cast turned over, and the empire that felt permanent to everything inside it was, from a great enough distance, just one more temporary arrangement of the sea, richer and longer lasting than most, but temporary all the same, as temporary as the empire that came before it and the one that came after. There is nothing bleak in this, I think, though it can sound bleak. It is simply the nature of the sea, and of time, and of life. Nothing is permanent. Everything is temporary. The rich, full, balanced ocean of the Mesozoic ran for 180 million years, and then ended, and the animals in it lived their whole lives without a shadow of that ending on them, and their lives were no less real, no less complete, no less worth living for being temporary. They hunted and were born and died in a warm sea, in full, every day, for longer than the mind can hold. And then it ended, and something new began, and that too will end, and something else will begin. That is not a tragedy. It is just how the sea works, and how it has always worked, and how it works tonight in the real ocean while you drift toward sleep. The animals down there now do not know they are temporary either. Nothing ever does. And it doesn't stop the water being full, or the lives being lived, or the sea going on, from age to age to age, always turning over, always temporary, always full. There is a strange afterlife to these animals that is worth telling, because it connects the vanished sea to the solid ground we walk on and to the buildings we live among. When the animals of the Mesozoic sea died, the countless ammonites, the belemnites, the plankton, the shellfish, the reptiles themselves, their hard parts sank to the seafloor and accumulated. Shells, bones, the microscopic armor of plankton, all of it settling, layer upon layer, over millions of years, compressing under its own weight into stone. The chalk of the great white cliffs of England and northern France is made almost entirely of the settled bodies of Cretaceous plankton. Trillions of microscopic armored algae, each one invisible, together forming cliffs hundreds of feet high. The limestone of countless quarries and countless buildings is made of the accumulated shells of ancient marine life, which means the Mesozoic sea is not entirely gone. It has been lifted up and turned to stone and quarried and built with. It is in the walls of cathedrals and town halls and ordinary houses across half of Europe and beyond. It is the white of the cliffs and the pale stone of the hills. The ammonites turn up in polished floors and countertops, sliced through and gleaming, their spiral chambers filled with crystal. The chalk that children write with on a blackboard is, quite literally, the crushed bodies of a Cretaceous sea. The animals we have spent tonight with are gone. Every mosasaur, every plesiosaur, every ammonite gone completely, 100 million years dead. But the sea they lived in is under our feet, and in our walls, and in our hands, transformed but not destroyed. When you next see a band of white chalk in a hillside, or a spiral ammonite set into a polished stone floor, or a cliff gleaming white above a gray sea, you are looking at the remains of the world we have been swimming through tonight. The warm, silent empire of the marine reptiles turned to stone, holding up our buildings, running under our roads, quietly everywhere, if you know how to see it. So let your breathing slow now. Let your shoulders come down from your ears. Let your jaw loosen. Let the weight of you settle into whatever is holding you, and let it hold you completely. You don't need to remember any of this. That was never what it was for. Nothing in that warm sea was ever remembered by anything for 180 million years, and it happened anyway. In full, every day, the dinner plate eyes opening in the dark, the long necks easing toward the fish, the young being born into open water and rising for their first breath. All of it real, all of it complete, none of it watched. If you drifted off somewhere back in the Jurassic, that's all right. It's still going on without you. It always was. Somewhere tonight, in the real ocean, the one that came after, the one that runs under everything eventually, the water is dark and cold and moving very slowly, and the descendants of that small hoofed animal are down there in the deep, filling the water with sound the reptiles never made, hunting in a dark that the ichthyosaurs once owned. The sea is continuous. It has never once been empty. Something always came down into it, and it was almost never the animal you would have guessed. It doesn't need you awake for any of that. Sleep well. We'll go somewhere else next time.